Welcome to Chapter 5, the Practical Python session. We've learned the theory. Now we'll implement a complete end-to-end workflow. We'll fetch data from Materials project, generate features with MapMiner, train models, and make predictions on new materials. This chapter is hands-on coding from start to finish. By the end of this chapter, you'll master the Materials project API for data acquisition and implement a complete machine learning pipeline. You'll gain practical skills in data fetching, feature generation, and model training. You'll also learn to compare against GNN baselines and implement hybrid composition plus structure approaches. Materials project is one of the largest open materials databases with over 150,000 computed materials. The API provides programmatic access to DFT-calculated properties, including formation energy, band gap, elastic moduli, and crystal structures. We'll use the MP-API Python client for efficient data retrieval. To use Materials project, first create a free account at materialsproject.org. After logging in, navigate to Dashboard and find your API key. This key authenticates your requests. Store it securely and never commit it to public repositories. The free tier provides generous rate limits for research use. Install the MP-API package using pip install MP-API. The main class is MP-Restr, which handles authentication and requests. Use the context manager pattern, with MP-Restr of API key as MPR. The materials.summary.search method is your primary data retrieval tool, returning properties for matching materials. Here's code for bulk data retrieval. Set energy above hull to filter for stable materials. Specify fields for the properties you need: materialid, formula pretty, formation energy per atom, and band gap. Use chunk processing for large datasets. Convert results to a pandas data frame for easy manipulation. Always validate your data before training. Check for missing values using isnull.sum. Plot histograms of target properties to identify outliers. Formation energy typically ranges within a few electron volts per atom. Band gaps range from 0 for metals to about 10 electron volts for wide-gap insulators. Remove or investigate extreme outliers. Now we'll build a complete machine learning pipeline from raw compositions to predictions. The pipeline includes data preparation, feature generation, train test split, model training, and evaluation. Each step is critical for reliable predictions. Start by converting formula strings to PyMatchin composition, objects using SDR to composition. Handle oxidation states if your featurizers need them. Filter compositions by element count if needed. Some featurizers struggle with single element or very complex compositions. Verify column types and clean any remaining issues. Use multiple featurizer to combine element property with Magpie preset and stoichiometry features. Call featurize dataframe to generate all features at once. This produces about 140 columns. The progress bar shows completion status. Check the output shape and verify no NaN values were introduced. Use Sklern's train test split with a typical 80-20 or 70-30 ratio. Set random state for reproducibility so you can recreate results. For classification tasks, consider stratification. The split must happen before any normalization to avoid data leakage. Report the sizes of training and test sets. Build a pipeline with standard scalar and your chosen regressor, such as random forest regressor. Use tuned hyperparameters or sensible defaults. Fit on the training data. Measure training time for benchmarking. Consider memory usage for large datasets. The pipeline handles scaling automatically. Predict on the test set and calculate metrics. MAE tells you the average prediction error in physical units. RMSE penalizes large errors more heavily. R² indicates the fraction of variance explained. Create a parity plot of predicted versus actual values. Analyze residuals to identify systematic errors. This slide shows the complete code from data loading to evaluation. All 5 steps are combined into a single, well-commented script. This is production-ready code you can adapt for your projects. A Google Colab badge lets you run it immediately in the cloud without local installation. Trained models are valuable and should be saved for reuse. Model persistence enables deployment, sharing, and version control. We'll use joblib for efficient serialization of Sklern pipelines. The saved file includes both the scalar and the trained model. Use joblib.dump to save your pipeline to a pickle file. The pipeline object contains all preprocessing steps and the trained model. To reuse, call joblib.load to restore the complete pipeline. Saved files can be several megabytes for tree-based models. Include version information in file names for tracking. Graph neural networks like CGCNN and MEG-NET use crystal structure information for predictions. They typically achieve higher accuracy than composition-only methods. However, they require structure data and more computation. Let's understand the accuracy-speed trade-off. For formation energy prediction, MAGPIE with XGBoost achieves good predictive performance. CGCNN with crystal structure achieves higher accuracy, roughly 1.5 times more precise. However, MAGPIE predicts 1 million compounds in minutes versus much longer for GNN. The speed advantage can be decisive for high-throughput screening. Band gap prediction shows a larger gap between methods. Composition-based approaches have higher error, while GNNs achieve better accuracy. Band gap depends more strongly on crystal structure through orbital overlaps and symmetry. This explains why structure-based methods have a larger advantage for electronic properties than for energetic properties. Choose composition-based methods when you don't have crystal structures, need high-throughput screening, or have limited training data. Choose GNNs when structures are available, accuracy is critical, and computational cost is acceptable. For many applications, composition methods provide sufficient accuracy at much lower cost. Why choose between composition and structure when you can use both? Hybrid approaches combine MAGPIE features with GNN embeddings for the best of both worlds. The combined feature vector captures both compositional trends and structural details. The hybrid architecture concatenates MAGPIE features with GNN-derived embeddings. Extract the penultimate layer from a pretrained GNN as a structure embedding. Combine with MAGPIE dimensions for a rich feature vector. Train a final model on the combined features. This can improve accuracy over GNN alone. Here's implementation code for the hybrid approach. Assume you have pre-computed GNN embeddings from a separate workflow. Use numpy.concatenate to join MAGPIE features with GNN embeddings. Train your final model on the combined array. Compare results to composition-only and structure-only baselines. For practical materials discovery, we need to predict properties for millions of candidate compounds. Batch prediction systems handle large-scale inference efficiently. We'll cover memory management, parallel processing, and result ranking. Start with novel compositions that weren't in the training set. Generate features using the same featureizer pipeline. Load your saved model and call predict. Rank candidates by the target property. Consider uncertainty quantification to prioritize high-confidence predictions for experimental validation. Analyze where your model fails. Identify compositions with high prediction errors. Check if certain element types or composition ranges have systematic errors. Use this analysis to improve your model through targeted data augmentation or feature engineering. Learning from failures leads to better predictions. Let's recap our journey through composition-based features. In Chapter 1, we learned fundamentals of converting compositions to numerical vectors. Chapter 2 detailed MAGPIE's feature structure. Chapter 3 compared databases and featureizers. Chapter 4 covered machine learning integration. Now in Chapter 5, we've implemented complete practical workflows. 5 major insights from this series. First, composition features are remarkably powerful despite using no structural information. Second, MAGPIE dimensions capture essential chemistry through statistical aggregation of elemental properties. Third, multiple featurizer options exist for different applications. Fourth, proper ML workflow with pipelines and cross-validation is essential. Fifth, understand the trade-offs between composition and GNN approaches. To continue your learning, explore our GNN Introduction series for structure-based methods. Study advanced ML techniques like Bayesian optimization and active learning. Apply these methods to specific domains like battery materials or catalysts. Try implementing papers from the literature to deepen understanding. Thank you for completing this series on composition-based features. Key resources include Mattmanner documentation at hackingmaterials.lbl.gov, Materials Project at materialsproject.org, and Ward's 2016 paper on MAGPIE. Visit AI Terakoya for more materials informatics content. We welcome your feedback and questions.